So welcome back. So in this lectures we are going to generalize the DC power flow and we have to analyze its sensitivity. So before proceeding to these current lectures, we just recall the previous lectures. So in previous lectures we already applied the assumptions and linearize the AC power flow equations in terms of the linear forms. And we have already applied these uh, assumptions on a 4-bus system. We can calculate the bus angles. So objective of this lectures, here we are going to apply these assumptions on the active and reactive power flow equations with the examples and DC power flow generalizations, and then we have to analyze this analytic sensitivity, and again we have to calculate the power transfer distribution factor, that is called the PTDF. So here the example again we have to take in. So in the previous lectures we have already calculated this admittance Y bus matrix in terms of the susceptance, and then we have to know this injection power in terms of the per unit already given. So we have know that. So bus 1 is 2, 1, minus 4, and then and consider that this is the theta 1, theta 2, theta 3, theta 4. So we want to calculate these. So we have to first take the inverse of this admittance or susceptance matrix. This is the inverse part. Then we can calculate simply, or we can first find out the inverse value, or we are simply apply the Cron reductions or LU factorization, or you can diagonalize these terms, this matrix. So using diagonalization or Cron reduction or LU factorization, we can solve the theta 1, theta 2 and theta 4. So here you can see this matrix should be a singularity we have to find, because in inverse we have to find first this matrix it is a singular or not singular. So this dependency occurs because all 4 angles are not independent. So you can see there, because the theta 1, theta 2, theta 3, theta 4. So these 4 angles are not dependent to each other. So they are depend to each other, because we can see that there is a difference. So what is important are the angular differences. Theta 1 is equal to a difference between 2 buses. Thus we have free to choose any one of them as a reference. So we have to take either first bus is a reference, or 2 bus, or 3 bus we have to consider. Suppose here we have to consider a bus having the 0-degree angles, and this difference value we can calculate other bus angles. So this angle is no longer with variable 0 degree. To fix this problem, we need to eliminate one of the equation and one of the variable by setting the variable to 0. We have to choose element first equation and first variables theta 1. Suppose in this previous equation we are putting the theta 1 will be a 0. So that is the reference value. So theta 1 we are putting the 0 and simplifying in the Y matrix. So 1 row and 1 first column. So we have to eliminate, and rest terms we are putting here. So theta 2, theta 3, theta 4 are the 0 for the solution. So we can apply this equation and we can calculate. So we can get power flow easily by eliminating just one terms by the summation in equation 11, which is already covered in the previous lectures, and give the power flow equation, that is a P kg. This is the B kj theta k minus theta j. When we are putting these values, so we can calculate the power flow between two buses, or we can say in a particular line. So this is the power flow in between 1 and 2. So when we are putting these value, we are getting this is the per unit. P13, so this much power. P214, this is the 0.25. 23, we are getting 1.25. P34 minus 1.25. So power flowing into the bus equal to power flowing out of that bus. And this power is nothing but this power Pkj is directly proportional to the current. So this is the Kj. So based on this power value, we can say that this is the equivalent to the current. So loading of this transmission line, or it is loaded or light loaded, we can calculate. So theta ij, which is already calculated. So these theta values we have put here and we can calculate. See here, the theta 1 is the difference value and theta 2, theta 3 we already calculated. So this is the 4-bus system. So here all terms we have given. So you know that this is the direction of the P12. So power flowing in this transformer in this direction. This is the P3. So in this direction, this 1 to 5, this is the direction, and 4 to 3, this is the direction, and 1 to 4, this direction. So each lines, what are the power flow, we can calculate using this DC power flow equations. So this is equivalent to the current. So here you can see this is the load. So load is that is demand already given. So these power flow equation at each transmission lines we can easily calculate and within a limited time frame. So DC power flow generalization, when we are going to generalize. So how we are going to generalize this algorithm? So we assume that we are given the network with following information. So we require this information when we are going to generalize the DC power flow. So total number of buses we have to know. How many number of buses are there? Then total number of branches is here. So total number of buses is represented by capital N, and total number of branches is represented by capital N. So bus number 1 identify as a reference bus. We have to give the reference bus. So generally we have to prefer bus number 1 is the reference bus. Then real power injection at all buses except bus 1. So we have to consider we have to calculate the real power injection all other buses except one bus, because one bus we are considering the reference, but that is the slack bus. So we are not going to calculate the injection power. So this one. Then network topology. So what are network connection from one bus to two bus, 3 bus? What are the line data are there? We have to calculate, and this must we have to know, and then admittances of each buses we have to know. Then we simply formulate the Y susceptance bus matrix. Then we can apply this form. This is the matrix form. So this is the P matrix. Then we have to take the B transpose. This is transpose means inverse into theta. So here P is the vector of the nodal injections for buses 2 up to N, and theta is the vector of the nodal phase angles for the buses 2 up to N, and B prime is we can see that this is the P matrix. A generalization of the B matrix developed is the follows. How we are going to calculate the B prime? So this calculation of B prime, we have to follow these 4 steps. So remove the J from the Y bus. We have to remove only the susceptance value from the Y bus or Y bus algorithm we already discussed. Then replace the diagonal element BKK with the sum of the non-diagonal elements in the row K. Suppose there is here 1K 4 non-diagonal elements are there. We have to add these 4 elements at a particular diagonal elements. So this is the terms. Otherwise we have simply multiplied by -1, that is the off diagonal elements, and multiplied by all diagonal elements by -1, and remove row 1 and row column in admittance matrix because we have already taken as the reference. So when we are getting this is the B prime. So B prime they have given. So then now come to the analytic calculation of the sensitivity of the DC power flow. So calculating the control sensitivities of by the repeat power flow solutions is a tedious and would require many power flow solutions. So because these are the actual in AC power flow, so these power flow equations are the nonlinear solutions. When we are plotting a straight line, so we can see that we are getting there lot of the possible solutions. Which solution is optimal, which solution is less sensitive, this is the very difficult to calculate. So an alternative approach is to analytical calculate these values. So what are the approach? They are just applying the few assumptions. This is the power flow between or from bus I to bus J. So this Pij we can say that magnitude, voltage and J by the reactance sine theta I minus theta J. So this will be equal to a theta value, and these value we are considering as equal to 1. So this is the one, this one. So we are getting the theta I minus theta J by the reactance. So this is the power flow equation. From the power flow equation, when we are applying these assumptions, we are getting these terms. So you can see that when we are changing the with respect to power change, so this is proportional to the angle change. So this is the angle change, this is the real power change. So we just need to get del theta ij by del pgk. So this is the del theta ijk. When we are combining, so this is the del theta ij. So this is the del by del pij. When we are calculating, so you can see del theta ij is divided by del pij is equal to, we can say this is the terms equal to xij. This is the reactance, this is the ij. So this is the sensitivity. So we can analyze the sensitivity with respect. So means this sensitivity is directly proportional to the reactance value of the transmission line. So if reactance value is going to change, so then this transmission line is the more sensitive. So it's going to affect in terms of the Ferranti effect or proximity effect. So it depends. So analytical sensitivity, then we have to calculate this theta ik. This is the B inverse in a real power mismatch. So from the first decoupled power flow equations, this is already applied. So we get the change in theta due to change in generation at bus K. So just set del Px equal to all 0 except a minus 1 at position K. So del Px we can put here the 0, and at the K bus we have to put minus 1 because we are just calculating at the Ks bus. So we have to put minus 1. Other change in the voltage, because these are the we are considering the magnitude voltage are the same, only the angle difference is a small value. So particular Kth bus, this value will be minus A because this power is the injected term. So we can say here del Pk. So not this is the injected terms, this is the power flow in the network. So that's why they are taking the power at a particular bus. So these are the analysis. For example, in the same way we are going to calculate. So suppose Z line is given J 0.1. So this is the J Y bus we have to calculate it, and then we have to remove first and these columns. So we can get this value B, and hence the change in generation at bus 3 we want to calculate. Then del theta 2 del theta 3. So we are calculating. So here we are putting the 0 and this is the minus 1 P. When we are multiplying or taking the inverse and multiplying, so we are getting this is the equation. So change in power in at bus number 3 to 1, so we are getting these terms, this minus 0 divided by 0.1. What is the reactance value? So we are getting this is the per unit. So from the del P to 3 bus 3 to 2, we are getting this is the value, and del P 2 to 1, so we are getting this much value. So this is the change in power. So you can calculate, this is the theta values we are already getting. So these theta value, because the theta 1 we already taken as a reference bus, this is the 0. This is the 3 bus system they have considered. And Z line they have given 0.1. So we have to calculate. So all the change in power due to the some disturbance in terms of the reactance we already calculated. So what is the power factor distribution, power transfer distribution factor, that is called PTDF. The power transfer distribution factor show the linear impact of the transfer of the power. So PTDF calculated using the fast decoupled power flow matrix B. So this is the theta B inverse P del Px. Same we have used here the equations. Once we know that the del theta, we can derive the change in the transmission line power flow, except now we have to modify several elements in del Px in portion to how the generation would participate in the network. In previous case, we are only considered the kth bus, the rest terms are the 0. But here in this case, we have to consider what are the generations roles in the network. Based on this, we have to calculate the power transfer distribution factors. So the same process we have to apply, only the derivation of the del Px matrix we have to consider here. So in this lectures we can summarize in terms of the active and reactive power DC power flow examples we considered, and we have to also generalize and also analyze the analytical sensitivity, and also we have to define the power transfer distribution factors. So this is all about this lectures. Thank you.